So we're going to talk about and introduce the Internet protocol and in general internets and Internetworking. First, by explaining what do we mean by Internetworking, motivate the need for Internetworking, and then look at one specific Internet work protocol called the Internet protocol. And maybe tomorrow we'll look at IP addressing. So what we know so far is that we have local area networks within buildings, within homes, and we have wide area networks that connect those local area networks together. So within the LANs, there are different types. Last week we saw there are different topologies, different medium access control techniques, different transmission media, and an organisation that builds their own LAN may choose something from a different organisation, depending upon their requirements. So if you think about all of the LANs across the world, they may be using different technologies, different and incompatible technologies. The LANs are mostly operating at layers 1 and 2. Sometimes we can connect two different LANs together. There are special devices called bridges that allow us to connect one LAN, maybe an Ethernet LAN, to a token ring LAN, or an Ethernet LAN to a wireless LAN. So we can do that in some cases. But in fact, bridges don't allow us to connect all types of LANs together. From the other perspective, over a larger area, we have wide area network connections that we use to connect LANs together over a larger distance. We may have point-to-point links as the wide area network, or even an entire network. So if I use a cloud to represent a local area network, say at our campus here. So this is all the computers on our campus here formed in a local area network, and we have our Rangsit campus. We have a LAN there. Of course they're separated by a large distance, but we'd like to connect them together so we can use a wide area network to connect them together. And there are different options. We need some special device attached to our LAN that connects via the wide area network to our Rangsit LAN. One option which we use is a WiMAX wireless link, where we have an antenna on at both locations, and really a point-to-point link connecting those two campuses together. So that's an example of a point-to-point, not ADSL or PDH, but a point-to-point wireless link between two LANs, uses a wide area network. That's one option we can connect our LANs. Another one is that we could pay an internet service provider to use their wide area network. So an internet service provider may have its own wide area network across Bangkok. I'll draw that. Need some more. So this is the ISP's wide area network. And in fact, maybe it's a packet switch network using a different technology than what we've covered. So it's made up of different packet switches, and they are connected together in some topology. And we can pay this organisation to carry our traffic between our two campuses by connecting into their network at both endpoints. And now we send our data to this device, which then the ISP delivers across their network to the Rangsit campus. So this is an example of a wide area network, but not a point-to-point link, actually an entire network. So we may use packet switching or circuit switching within this portion of the wide area network. The devices that are interconnecting these LANs and wide area networks need to support both technologies. This device needs an interface that supports the LAN technology and an interface that supports the wide area network technology. Okay? So this one needs to be compatible with both, because it effectively transfers or translates between this technology and this one. We send our data across our wired LAN, it reaches here. This one transmits it across the wide area network using the specific technology in here. So we know that we'd like to connect LANs and LANs together via wide area networks. And that the organizations that build their LANs and the companies that offer wide area networks may choose different technologies. So the technology used in this LAN, in fact, may be different from this one. And we see here two wide area networks using different technologies, a wireless link and a packet switch network. What we'd like to achieve is to allow any computer, no matter what LAN or wide area network they're attached to communicate with any other computer. So we'd like to be able to allow communication between end user devices irrespective of what technology they're using in their directly attached network. And that's where Internetworking comes in. Internetworking is the concept of connecting many different types of LANs and WANs together in order to allow any computer to communicate. So this is an example of Internetworking. We have different technologies in the individual networks. We connect them together using these special devices here to create one larger network, an internet, that allows any computer on any network to communicate with any other. That's the goal. So Internetworking, connecting individual networks together. Here's a larger example from expanding from here where we hide the details of the individual components and just draw them as clouds. So that's a common way to draw an individual network. It may be a wireless LAN, it may be a packet switched wide area network, maybe a switched star topology LAN here. We don't really care when we're looking and talking about Internetworking. They may be different technologies inside these clouds. We connect those individual networks together via these special devices, these black ones here, which we refer to as routers. So a router is a device that connects two or more LANs and WANs together. This router is connecting two different networks. This router is connecting three. Normally they connect two or more together. Routers are packet switches. So if we look at this network as a whole, it's a packet switch network. We may have some hosts, some stations on these LANs. If we want to get data from a station here to a station here, just remember how packet switching works. We send to a switch, that decides to send to another switch, to another switch, to another switch until we reach the destination. So we use the concept of packet switching to deliver our data in this internet. Specifically, the routers are packet switches that operate at the network layer. So we've now moved from the physical and data link layer to talk about concepts at the layer 3, the network layer. On the next slide, we introduce some more concepts. Let's explain them. We connect our local and wide area networks together using routers. So we connect multiple networks together to create one large network. So connect many networks to create one large network. We often may refer to the individual networks as subnetworks. They are subnetworks of the larger network, or in short, subnets. So this is one subnetwork. This is another subnetwork. We have 9 subnets in this example. And the entire network we will refer to as an internet. So we have one internet in this example which contains 9 subnets. And the subnets are connected via routers. The subnets may use different technologies. What else do we say in terms of terminology? So routers connect our subnets. An internetwork or an internet is the whole network, the entire network. Internet is just short for internetwork. We'll sometimes distinguish between a general internet. If we go and build this network, we can call it an internet with a lowercase I. But the internet with an uppercase I usually is used to refer to the network that we attach to on a daily basis and communicate with everyone else on the world. That is a specific internet. This is the general concept of an internet. You can go into your home, get some computers, connect them together, and build your own small internet, lowercase I internet in your home. It has no attachment to the outside world, to the larger internet, uppercase I. So an internet is just a concept of when we connect many subnets together via routers, we get an internet. I think the rest of the concepts we already know. It's just recapping on things that we know. We have a packet switch network, and the 2 processes that we need in a packet switch network is we need to be able to discover a path from source to destination. Routing does that for us. And once we know a path, we need to be able to send the packets through the path. That's forwarding, the process of forwarding. And of course, they directly relate or directly connected because in routing, the end result is that we create routing tables. In forwarding, we read those routing tables to determine who to send to next. We've already spoke about the differences between packet switches and circuit switches. A packet switch is a generic device that performs switching of packets. It may operate at the data link layer or at the network layer. What we're talking about when we talk about routers is packet switches operating at the network layer. No. No. We have another switch, another type of switch. Last week we introduced star topology LANs, and this central device was either a hub or a switch. Let's refer to that device as an Ethernet hub or an Ethernet switch. It does the general process of switching. Packets come in and it switches on one of the output ports, but it's operating at layer 2, a specific type of switch. It operates only on Ethernet frames. So it's a general switch, but it's not a router. So one way we may distinguish is we refer to an Ethernet switch or a LAN switch. That's what we referred to last week. If we look at a packet switch, well, an Ethernet switch is a case of a packet switch, and a router is a case of a packet switch. But a router and an Ethernet switch are different because a router operates at network layer, layer 3, an Ethernet switch operates at the data link layer, layer 2. They operate on different protocols. So some terminology for what is internetworking? Connecting multiple subnets together via routers. What we want is that if we have our network, all right, this is a simple case with 2 LANs and 2 wide area networks, but across the globe we have many LANs, many wide area network connections, allow any computing device to communicate with any other. And we need normally an internetworking protocol to support this. So there are a number of issues that we need to address to achieve this aim of allowing anyone to communicate with anyone. And that's what an internetworking protocol aims to solve. So a general internetworking protocol, some of the things that it may need to do, all right, it needs to provide links between subnetworks. So somehow we need to connect one subnet to another, which is a router. So an internetworking protocol needs to be implemented within a router. And we'll see that when we look at a specific internetworking protocol. So we need to be able to connect them together somehow. We need to be able to provide for routing and delivery of data between end user processes on different subnets. I have my PC here, and I have an application running on it, which is really a software process, and I want to communicate with another application across here, another software process. To allow that, we need some mechanisms so that my application, when it sends data, it can deliver it to the application here, the software process on this computer to this process. So we need to allow some way to communicate between software processes on the end computers. So just the general things that we need an internet working protocol to do. Often we'd like to keep track of the usage of the networks. This computer sends across the LAN, and then the data goes across another wide area network. In this example, owned and operated by someone else. So it makes sense that this network operator would like to keep track of how much is this network being used by this organisation, so they can charge them some money at the end of the month, for example. So keep track of the network usage, and if things go wrong, keep track of that. So if we can monitor the status of this network, maybe there's a failure at one of the points in the internet, then we'd like to be able to monitor and maintain some status information about how the network is operating. And because we need to deliver data across subnets that use different technologies, our internetworking protocol needs to handle these differences. So some of the differences that we encounter are listed here. Maybe a simple one. Different subnets may specify a different maximum packet size. If you recall back to last week when we spoke about Ethernet, and towards the end we gave the structure of an Ethernet frame, and it had a header, a trailer, and some data in the middle. And the maximum amount of data that could be included was 1,500 bytes. So any frame that we send across this subnet cannot contain more than 1,500 bytes of data. That's a characteristic of the protocol. We cannot change that. Different technologies may have different maximum packet or frame sizes. This one may be 1,500, this one may be 500 bytes. So different technologies will make trade-offs as to what's the best for their specific purpose. That creates a problem. This application wants to send data to here. Let's say it has 6,000 bytes to send. Then it knows this application is attached to a LAN. It knows the technology used in the network it's directly attached to. So it would know that the maximum size to send across this subnet is 1,500. So it breaks this into 4 frames. 6,000 bytes of data, we would need 4 frames using the maximum size of 1,500. And then we'd send them across our LAN. We'd send them to the next device in the path, say here. And now this one receives it and realizes, okay, receives the first frame, and it is 1,500 bytes in length, but realizes, okay, over this network we can only send frames of a maximum size of 500 bytes. So we'd need to break that up into 3 separate frames. And similar for the second one. This process of dividing the frames up into smaller chunks, fragmentation, can incur a large overhead. We'd like to avoid this as much as possible, because every time we divide it up into a smaller frame, there's some processing overhead, and there's a header included on every frame. The smaller the frame, the larger the contribution of the header towards the overhead. So we'd like to avoid this. So an Internetworking protocol needs some rules as to how to handle the fact that different subnets may have different maximum packet sizes.
This maximum packet size is the NTU when you configure.
In practice, the maximum packet size is sometimes referred to as a maximum transmission unit, an MTU. You may see that on your computer, which is across a path. If we know, okay, this is 1,500, this is 500, if this was 1,000, the maximum we should send is 500. The minimum, in fact, of those 3. In order to avoid this process of fragmentation, we will spend a few slides talking about how to do this, or different options of how to fragment the frames across our internet. So it's just an example that subnets have different maximum packet sizes. We need to deal with that in an Internetworking protocol. We will look at how IP deals with that towards the end. Another example, addresses. Let's just make it a bit clearer. Again, different subnets may use different addressing schemes, different address formats. We saw last week the example of the 48-bit address that your computer has if it's attached to a LAN, a wired LAN, an Ethernet address. I will not write a 48-bit address. Let's say that on this subnet we use the address format where devices attached use an uppercase letter. This device is device A. This device is attached, it's device B, and this one's also attached at C. And maybe we have another computer, which would be D. So just to keep it simple, let's say that the devices attached to this LAN use the format of an uppercase letter. The data link layer protocol on each of these devices understands these formats and can send to anyone on this subnet because it understands the formats of the addresses, the addressing schemes. On this LAN, maybe we use a different technology and a different structure of addresses. Let's say that they are numbers. This is number 1, 2, 3, and maybe another host, 4. Different addressing schemes may be used in different subnet technologies. Our goal is for this device to communicate with this device. When we want to send data to someone, we need to know their address. We need to be able to create a packet and include in the header of that packet the destination address. But in this case, they're using different address formats. If we want to send data from A to 1, in fact, A does not understand any other address format except for uppercase letters. So this may be a 3-bit number, this may be a 5-bit number. Different format, and this one does not have the software or hardware to implement it to understand any other format except for what it uses. This may be, instead of at Rungsit, it may be on the other side of the world we want to communicate with. So different subnet technologies may use different addressing schemes, and an Internetworking protocol needs to handle that. We want to allow these two devices to communicate even though they use different address formats. And the approach that we'll see that the Internet Protocol uses is to give these devices another address which uses the same format. For example, this device has the MAC address or hardware address A, and it would obtain a different address. Let's say it's lowercase letter and followed by a number, A3. And this device would get a second address using the same format as this one. Maybe it's C5. These two addresses, A3 and C5, are examples of Internetwork Protocol addresses. They are addresses assigned to the end user devices so that we can communicate across different subnets that use different addressing schemes. We'll see that that's what the Internet Protocol does effectively. It gives devices a second address. So now when this one wants to send data, it knows and understands the format of the destination address. It can create a packet, source equals A3, destination equals C5, send it via packet switching through the network. So all the differences between the different subnets should be handled in an ideal case by an internetworking protocol. Things like security. Some subnets may have different security mechanisms in them, and if we want security from the source to destination, our Internetwork Protocol needs to handle that. Error recovery, which is what happens if there's a packet loss or bit errors. This subnet may be using stop and wait. This subnet may be using selective reject. This link may be using no error recovery. It's just a design of the link that there's no error recovery. So with stop and wait, we can transfer across this subnet and high chance that our data will be delivered. But then when we transmit across this subnet, then we may have errors and our data will not be delivered because it has no error recovery. So even though some subnets may have error recovery, others may not. So what if we want to have error recovery from source to destination? That is, I want to be certain if I send data, the destination receives it. I can be reasonably certain if I send it across this subnet, it will get to here. If it's sent from here to here, it will be delivered. But I cannot be certain that it will be delivered across this subnet. So because the different component networks may have different error recovery schemes, our Internetwork Protocol needs to handle those differences. And one way is to have another error recovery scheme between the source and destination. We'll see an example of a protocol that does that. So, some of the requirements of any Internetworking protocol. The most commonly used Internetworking protocol today is called the Internet Protocol, IP. IP meets some of these requirements, not all of them. It doesn't do all of these things that we listed here. The things that it doesn't do, which are considered important, are handled by different protocols as part of the TCP/IP stack. ICMP, for example, handles maintaining status information, error reporting. TCP handles error recovery. IP does not. So the Internet Protocol is one internetworking protocol, and it handles some of these features, but not all. It leaves some of them to other protocols. So we're going to spend some time going through IP. So IP is the internetworking protocol used in the internet today. It's the most commonly used internetworking protocol. There are others. IPX was an old one, still around in some networks, but mostly replaced by IP. X25 and there are several other internetworking protocols used in the past, but most of them are not used in new networks today. In fact, IP, there are different versions. It is maybe 30 or 40 years old and has improved over time. The version that we're going to talk about, and the main one in use today, is IP version 4. There's an update available, or a new version, IP version 6, and that's available and used in some networks, but not widespread. Maybe in the next 3, 5, 10 years, IPv6 will be more widespread than IP version 4. We don't have time to cover both. We're just going to look at IP version 4. Initially developed in the US and became an internet standard, and the standards organization that maintain and develop this standard is called IETF, the Internet Engineering Task Force. Last week we saw IEEE created the Ethernet standard. IETF have created many internet standards like IP. What does it do? The features of IP. It's a connectionless protocol. It does not establish some connection from source to destination to transfer data. It's a network layer protocol and a network layer internetworking protocol. So it provides internetworking. And importantly, it uses datagram packet switching. So we've seen these concepts before. That is, to deliver data from source to destination, there's no connection created. It simply creates a datagram, sends it to the next device in the path, which sends it to the next device, and eventually to the destination. That's our datagram packet switching, where our routers are the packet switches. So using datagram packet switching, it provides data delivery across the network. Okay, it delivers the data from source to destination, or it attempts to. It provides addressing. So this concept that we just gave as an example, where these two devices get an extra or a second address so that they can communicate, that the format of this address is specified by IP, the Internet Protocol. It's an IP address. This is an example. It's not a real IP address. It provides fragmentation and reassembly. This thing that I alluded to about this subnet supports 1,500 byte frames. This one only 500 bytes. How do we handle that? IP handles that using fragmentation and reassembly, which we'll go through. And in fact, that's all that IP does. It's relatively simple protocol. It doesn't provide features like setting up a connection. There's no concept of saying, send a special message to the destination saying, I want to communicate with you, and get a response back, and then send data. We do not do that. IP is connectionless. There's no connection. IP does not provide error control or error recovery. If we send an IP datagram through our internet, and if it doesn't get to the destination, IP doesn't care. There's no concept of an acknowledgement coming back. There's no concept of forward error correction. It just sends the datagram, and what's called a best effort service, it makes its best effort to deliver, but it provides no guarantees. If something goes wrong, it will not try to retransmit. So it provides no error control, no flow control. There's no concept of controlling how fast this sends, such that it doesn't overflow the receiver. It doesn't do that. In fact, those three mechanisms are not provided by IP. If you need them, if your application needs them, then a transport layer protocol, TCP, does provide them. So if you want to make sure your data gets from source to destination, IP will not do that for you, but there's another protocol in the transport layer that can do that for us, TCP, which we'll look at in the next topic. It does not provide any status reporting, any link errors and so on. In fact, there's another protocol that does that for us, ICMP. It provides no priority of different packets being sent. I send my packets across the internet, and I'd like them to get higher priority than all the students' packets sent across the internet. That is, I would like mine to get there first. IP does not do that for us. There are some other mechanisms that can try to provide priority, but that's not built into IP. And it provides no security mechanisms. There's no concept of encrypting data in IP. There's another protocol that introduces that, IPsec. So, in fact, IP is very, very simple in terms of the mechanisms it provides. Send packets or datagrams, provide some addressing, if necessary, fragment and reassemble. The simplicity of IP contributed to its widespread use. Because it's easy to use in different subnets and easy to implement in different devices, it's become widely used and implemented in almost all devices nowadays. This illustrates our 5-layer stack, giving some example protocols from the lower 2 layers, things like Ethernet, wireless LAN, different wide area network technologies, and many others here, just some examples. At the network layer, we have IP, the Internet Protocol. That provides internetworking. There are some supporting protocols. We mentioned ICMP does some status reporting. That's part of the network layer, but separate from IP. There are individual routing protocols that we can consider part of the network layer. And then above that, we have protocols for, as part of the transport layer. TCP is one example, UDP, there are several others. And at the top, we have all our protocols that support specific applications. For web browsing, for email, for network management, for domain names, instant messaging, voice, video, all our different applications may have an application layer protocol here. So in the internet today, the one thing that's common in all devices attached to the internet is IP. And in fact, that's the core protocol in the internet. So what we do in IP is we create an IP packet, or more precisely, an IP datagram, and send that from source to the destination. Let's look at the structure of this IP datagram. When we've drawn packets before, I've normally drawn them like this: header and data. So to visualize a packet is, in general, is just a sequence of bits with some structure. The header has different fields. And the data is whatever we're wanting to communicate. This is another way to draw a packet where we show the fields in the header. And the way to read this diagram is that we read row by row. That is, here's a row, this is the header, and followed by the data. And in this example, each row represents 4 bytes, or 32 bits. So if we give the numbers from 0 up to 31 in terms of bits. So 4 bytes of information in the header, and then the next 4 bytes, and the next 4 bytes, and so on. So it's just a way to visualize the structure of this header, the set of fields included in the header. Let's go through these fields. Some of them will explain in a bit more depth than others. First, the first 4 bits of every IP datagram contains the version of IP that we're using. And in this course, we're assuming version 4. So it would have a 4-bit number. What is what? 0100. Version 4, a 4-bit number indicating the version of IP that we're using. So that when a router or a host receives this datagram, it knows, okay, what I've just received is for IP version 4, not IPv6, it's IP version 4. Our header in an IP datagram by default has 20 bytes of information because each row is 4 bytes. We have 1, 2, 3, 4, 5 rows. The default size of the header is 20 bytes. But in fact, we can have some optional fields. We may choose to include other fields. So the header length may be variable. So the second field indicates the length of the header. So use some number to indicate how long is the header. Normally it's just 20 bytes, but if we have options, it may be larger than 20 bytes. Hence we have the header length, so that when someone receives this datagram, it knows where is the split between the header and the data. The next two fields, diffserv, ECN, are used in very special cases. I said before the IP doesn't provide any priority, but other protocols may use these fields in the IP header to provide some sort of priority between different datagrams. So it's an extension or a way to indicate priority between different datagrams. We're not going to talk about these concepts of diffserv or ECM in this course. Next is the total length of the datagram. The datagram has header plus data. The data size may be variable. This field indicates how big is the datagram, so that the receiver knows where does the data finish. The maximum size of the datagram is 65,656 bytes. That is the size of the header plus the data. Because the total length is a 16-bit number. So we indicate the size of the datagram with this field. The ID or identification field is like a sequence number. So we can include a sequence number for our datagrams that we transmit. If I transmit 10 datagrams, I may start at 0, increment through to 9. So it's like a sequence number, an ID of that datagram. A flag is, in general, a 1-bit value. The flag is either off, set to 0, or on, it's set to 1. It's used to indicate some meaning of this datagram, or some feature is on or off for this datagram. In the IP datagram, the flags, the main use of the flags is for fragmentation and reassembly. This concept that we send a datagram, we may need to break it into smaller datagrams, fragment that. If we do, we'll use these flags and also this field of fragment offset. We'll see an example of those in use in the later slides. Time to live is an 8-bit value that indicates how long this datagram has to live in the internet. Remember when we looked at flooding, we introduced a hop limit. We transmit with a hop limit, initial value 4, we send it to the next device, it reduces to 3, to 2, to 1. Once it gets to 0, we no longer transmit. That packet had a lifetime of 4 hops. With a hop limit of 4, it can transmit across 4 hops. Same concept for time to live. That's how time to live is used. We set to a value 4 here at the source. We transmit to the first router, it decreases it to 3, the next router to 2, to 1, to 0. Once it's 0, it will not be transmitted in the internet anymore. So it disappears from the internet. So it's some limitation of how long that can be transmitted in the network. The protocol field indicates what type of data do we have in here. If we go back to this diagram, Remember, the process is that we take data from the application, put it in the application layer protocol, send it to the transport protocol, and that sends to IP. The protocol field in the IP header indicates which transport protocol sent the data to IP. TCP or UDP or something else. So if the data in here came from TCP, the protocol field in the header would have a value that indicates that the data comes from TCP. And there are some constant numbers to indicate different transport protocols. TCP has the value, I think, 6. These numbers are predefined as, okay, TCP corresponds to protocol number 6. Therefore, in the protocol field, we would include the value 6. UDP is 17, and other protocols have different numbers. So this protocol field indicates what's the higher layer that generated the data. We have a header checksum. Remember, a checksum is used for error detection. We include some extra information, and the receiver checks that against the received value to determine if there are any errors. This header checksum is applied, as the name suggests, just across the header, not across the data. If we transmit an IP datagram and we receive that, then the receiver checks, does the checksum correspond with what was received in the header? If there was some error in the header, one of the bits was changed, this checksum should be able to be used to detect that error. But if there's some error in the data, the checksum cannot be used to detect that error. It only detects errors in the header.
What if checksum contains error itself?
Same with the parity check. If you remember back to the parity check, it doesn't matter if it's the parity bit that's in error, we can still detect that error. So if the checksum contains an error, then the receiver will detect an error, because the checksum will not match the application on the rest of the header information. So going back to initial parity check, if we had 7 bits plus a 1-bit parity, if there was an error in any of those 7 bits or the parity bit, the receiver would detect some error. The same can be applied here. It's just a different checksum algorithm. And then, perhaps most importantly, we have the address of the source device and the destination device. These are 32-bit IP addresses. We'll spend some time going through the structure of these IP addresses, but as a simple example, it's the address given to this device by the Internetwork protocol and to this device. And in our IP datagram, these normally do not change. They are the address of the original source and the final destination. We create the datagram at the source. We send it via the routers, the packet switches. So we send it to here, to the next one, and to here. It doesn't change as we send it via these packet switches or routers. So the address indicates this and this. Even though the source is here and the destination is here, we send it to this device first. That's not what the address indicates. It's just the original source, final destination. The options may be included if there are some extensions to IP to support different features. So there's an opportunity to include extra fields to support different options. And then we have the data. So we're not going to go through any options. We'll assume in most cases there are no optional fields. It's just our 20-byte header plus the data.
About the time period, when we subtract, when it reaches the router or when it's
the time to live field set by the source host, let's say set to the value 10 and is sent. When it's received with a value 10, decremented, and then sent if possible, I think. That is, decreased to 9, it's not 0, send.
So when the packets arrive, the router will decrease the time to live and then checks whether it is...
Yes. So that means if we set it at 10, it should cover 10 hops. You'll see in past exams that this information was given. But in some cases, you need to understand what information is in, what does it mean by source and destination address? Does it mean this device and this device, or does it mean the address of the router? Well, it's in fact the original source and the final destination. We'll see some more examples of addresses tomorrow. This lists those fields in a bit more depth. What does IP do? We said it's a connectionless protocol. We'll use connectionless internetworking. The alternative is connection-oriented. And we know these concepts of a connection or no connection when we looked at circuit and virtual circuit packet switching. If we were using a connection-oriented protocol, before we send data, we would establish a connection with the destination. Send a special message saying, I want to communicate, get a response, and then send data. IP does not do that. IP just sends the data, connectionless. There's no concept of setting up a connection or terminating a connection with IP. We just send our datagrams. Those datagrams are treated independently. The first datagram and the second datagram, the packet switches, the routers may treat them differently. This connectionless concept is much simpler. We don't have this overhead of setting up a connection and can support any type of application. If I want to create an application between source and destination and I want to set up a connection, then my application or transport protocol can do that for me. IP will not do it for me, but another protocol could. If I don't want a connection, I can immediately just send as IP datagrams. So it's very simple to support both types of applications, whether we want a connection or not. Very small overhead if we use things like UDP and we don't need a connection from source to destination. Some more terminology. The devices in our internet, remember we are going to start to ignore the details of inside these clouds. The technology within a WAN, a wide area network, or a local area network, we know about, but when we talk about layer 3, network layer, and internetworking, let's ignore the details of how they're built. We just treat them as clouds, as subnets, and we have hosts attached to subnets and routers connecting subnets together. The hosts are the end user devices, the stations. The routers are the datagram packet switches. Some differences, or some common differences between hosts and routers. Host usually only uses one single network interface at a time. My laptop is a host. How many network interfaces does it have? More than one? More than two? What are those network interfaces? Don't give me a number. What are the network interfaces you would expect my laptop has? Ethernet, a wide LAN, wireless LAN, has a Bluetooth interface as well. So my laptop has 3 network interfaces. But normally I only use one at a time. I'm currently connected to the wireless LAN. In fact, I don't have to use one at a time, but most operating systems would and most applications just use one at a time. If I plug in the wired LAN, I'll start to send data via the wired LAN. So normally a host only uses one interface at a time. It's possible to use more than one, but that's the most common case. A router has two or more interfaces. Some hosts only have one interface. Maybe I don't have wireless LAN. I've got an old laptop. I can only plug a cable in. Or my PC normally has one interface. A router normally has two or more interfaces because what a router does is connects different subnets together. It needs at least one interface for this subnet and another one for this subnet. And it would normally use them at the same time. It can be receiving data on this interface and at the same time sending on this interface. A host does not forward IP datagrams, a router does. And this is the primary thing that distinguishes between a host and a router. By forwarding a datagram, we mean receiving and then sending on. A host creates datagrams and sends them. This host creates a datagram and sends. This router receives and forwards on to the next router. This router receives and forwards on to the next host. This host receives and consumes that datagram. It doesn't send on to anyone else. And that's the thing that distinguishes between a host and a router. Host never forwards datagrams. A router can forward datagrams. What's my laptop? Host or router? What's your tablet? Okay. Does it have to be? In fact, by default, your normal end computer is a host, but in fact, to turn it into a router, in software, we can configure it to allow forwarding. So next semester in our lab, we'll show how to change the software, the operating system, so that your laptop can become a router. That is, it can receive and then send on. So it's very simple, in fact, to change any computer from a host to a router, just to enable forwarding and go back to disable forwarding. So it's not so much about the devices, it's about whether the device is allowed to forward or not. Of course, hosts, because they cannot forward, are either a source or a destination. They cannot be the intermediate device. A router, it does forward, but a router can also be a source or a destination. That is, I send from this host to this host. I could potentially send this is the source to this router as a destination. There's nothing to stop that. And it's used commonly to manage the different devices. So even though a router does forward datagrams, it can also act as a source or a destination, but not as common. It's mostly forwarding data. Anyone have ADSL at home or in their room? You've seen an ADSL modem. All right, you plug in the telephone line into the modem, and then you plug your computer via a wired LAN interface into the modem. So that modem is acting as a router. It's connecting the subnet of your LAN to the subnet of or the wide area network for the telephone network. So that's a router. And sometimes if you want to configure that router, you would open your browser and type in some special address like 192.168.1.1 or something. That is sending from your computer, sending IP datagrams from your computer to the router to manage that router. So that router, when you're sending to Facebook or wherever, that router is forwarding your datagrams, but that router can act as a source and destination, especially if you want to manage that router, to configure it. We know this from before. IP routing is the process of finding the routes through our IP network. IP forwarding is the process of delivering that datagram via those routes. And we use routing tables. So the same concept when we spoke about routing in packet switch networks. IP routing creates routing tables. IP forwarding uses those routing tables to determine who to send to next. We'll go through this slide after we go through a few other concepts. In terms of IP routing, the Internet Protocol does not specify what routing protocol to use. It allows you to use any routing protocol. IP is about forwarding the data. How to find the best paths from source to destination, there are different routing protocols you can use. Some of the acronyms or names are listed here. Many different routing protocols. They have different features like different strategies, different metrics used, different algorithms used. So there's no single routing protocol needed in the internet. There are multiple different ones. But as we've seen before, the process is that each routing protocol creates and updates a routing table. And each device in our internet, both hosts and routers, store a routing table. The routing table stores information to determine the path from source to destination. And we saw that it doesn't store the entire path, it stores the next hop in the path. That is sufficient. So that makes the routing table simpler. That's this concept of storing next hop routes. Don't store the entire route. It makes the routing table smaller and easier to manage, update. So some routing protocol puts the data into the routing tables. Hosts and routers have routing tables. And IP, the Internet Protocol, uses the information in the routing tables to determine who to send to next. This host would have a routing table. If we have some data to send, an IP datagram would be created. We look in the routing table to determine, okay, we need to send to this router to reach the destination. We send it to here. This router looks in the routing table, realizes we need to send to this router to reach the destination, and then eventually to the host at the destination. So that's the same concept we've covered in routing in general. It's used in IP. We can simplify the routing tables even further. We saw one simplification where we store the next hop rather than the entire path. So we simplify the routing table in that way. There are two other techniques to simplify the routing table. Let's go through them later, because I think we won't have time to cover both of them. Any questions on IP so far? There's much more to go, like how routing works. We'll go through an example of routing tables. We'll go through how this works. Any questions so far on the structure of an IP datagram? Everything's okay? This is one of the larger topics and more important ones. Any questions? In preparation for your quiz, is there any questions? There's a quiz now, in the last 10 minutes.